Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Quadric with Nigel Drego. We're going to talk today about changes in chip architectures at the edge. Nigel, when you get to the edge, the processor architectures that exist in the cloud no longer apply. They just take too much power. They don't really need that much performance. So what do you have to keep in mind? What sort of constraints are you working under?
Yeah, great question. I think you said part of it yourself. So if you look at what NVIDIA or AMD or Intel or any of these players build for the cloud, they're high power, yes, but they're going after massive throughput. At the edge, what you really want is something that is power efficient and provides high performance in the form of low latency. Because if you think about edge applications like a self-driving car, robot, those are things where you need to react very quickly. You don't have time to transmit data to the cloud, wait for a response. You have to be able to run AI models or more generally software very quickly, performantly, and efficiently on a device at the edge.
Let's take a closer look.
Sure.
Nigel, what are we looking at?
All right, so up here I have a very simple block diagram of what typical architectures for edge applications look like. Typically you have a legacy core, something like a CPU or a DSP, think an ARM Cortex-M or a Tensilica DSP, and then that is paired with an NPU, a neural processing unit. That's because most applications at the edge today are looking for processing or the ability to process AI.
What does an NPU do differently than a CPU or a GPU?
Great question. An NPU is highly optimized for matrix multiplication or convolutions, which are really the fundamental operations that are within most AI models, if not all. And so most people build a highly optimized NPU, and then that takes care of a good number of the operations in the model, but you have a legacy core off to support all the other kinds of operations in that model.
And so you have a mix of processing elements in here too, right? You may have a GPU and a CPU as well as one or more NPUs, right?
That's correct. So in most architectures, this would be the simplest block diagram. In most, you'll actually have a GPU and a collection of NPUs and even maybe a collection of CPUs to achieve the kind of latency or throughput considerations that you have for a particular application. Right?
The problem here is that you have to partition whatever you're doing. Whatever problem this is, you have to partition it into the best places, right?
That's right. And this was a problem that we originally saw back in 2016 when the three of us co-founders started to build a robot. We really thought that robotics was going to be a big part of the future. We started to build a robot. We were using, at the time, NVIDIA GPUs plus CPUs. And what we found is that partitioning problem is actually pretty difficult. To get it right, both in terms of software as well as performance, you have to do a lot of work. And this is even with an NVIDIA GPU where you have a lot of unified compute. So, you would rather not have an architecture where you have to split the problem into multiple places. What we at Quadric have done, we have taken this entire thing and created a single architecture that combines the best of both of these worlds with changes to both of them in a proprietary ISA. So a new architecture, proprietary ISA, that allows for high performance, high efficiency, low power, at the edge compute.
And the key problem here is latency, right?
That's right. In most edge applications, you care about latency, not throughput. And that is a fundamental difference between data center applications and edge applications. When you talk about latency, you have to worry about how data transfers between the multiple elements in your compute subsystem. If you have a single compute element that is capable of doing all of the compute that's required for that application, you end up moving less data around, you go off chip less, and so both from a power and a latency perspective, it is a win.
So all this has to be tightly integrated together, right?
Correct. Our special sauce is that we take the CPU portion, the ALU and the compute portion of this legacy core, and we integrate it very tightly with the NPU portion, or the multiply accumulates that have to be done in a matrix multiplication. So those are very tight. We include memory in each of our processing elements so that data is moving very little away from the compute.
So these are soft cores, right? Do you foresee that at some point these will be chiplets as well?
Yeah, I think the IP market as a whole is moving in that direction. As packaging costs come down, I think IP providers will really become chiplet providers for a lot of different kinds of IP. Today, however, we do provide all of this as soft cores.
Let's go back here for a second. So what your big problem here is that moving data is the most power intensive part of anything, right? It's not so much even the processing. Processing is you can refine, but moving that data is very costly.
Absolutely. You hit on the fundamental part and problem of the AI compute problem. An NPU really wants to do multiply accumulates, but you have to be able to provide data to all of those multiply accumulate units. If you're always coming from off chip, that is a huge, probably 2 orders of magnitude difference than keeping that data local. So you really want memory that is close to the compute, and there are some architectures that even try to do it within the memory, compute within the memory. Ours is a near memory compute architecture, which means that you're expending a lot less energy because the data is right next to the compute than having to go off chip repeatedly.
And there are other tricks that you can throw in here too, right? Like branch prediction and basically prefetch of some of this stuff.
We absolutely do a lot of data prefetch. The nice thing about a lot of AI processing is that you know all of the memory access patterns ahead of time. And as a result, you can optimize both the architecture in terms of the memory subsystem, as well as the software, to be able to take advantage of those known compile time memory access patterns.
You're trying to integrate multiple different elements here. Do the tools and the flows that are out there today support this?
Yeah, in fact, for us, because it is a single core, a single unified core with processing, just simple processing elements, we use all the standard EDA flows that exist today. We provide those as reference flows to our customers, and so there's nothing really special. If you can design a chip, if you can design digital logic, and you have access to standard single port SRAMs, you can implement our Chimera GPNPU.
The hardware is just one piece of this. You've also got algorithms, and those algorithms are almost in constant change and flux, right?
Absolutely. One of the fundamental premises that we had when we were founding this company is exactly that, that the state of software at the edge, the state of AI, is changing so quickly that if you were to go design a very specialized piece of hardware for what you saw today, you would likely be obsolete by the time you got that in silicon. As a result, we made the fundamental choice to have something that we call a general purpose NPU, so that when you have a new model that comes out, even if our graph compiler doesn't support a particular operator or particular structure, you have the ability as an end user to program the entire thing, because it is programmable, to achieve that functionality. And while you could do that with the legacy core, you're often limited by how much parallelism exists in a CPU or DSP. Whereas in our architecture, you have the entire parallelism. You have, in our largest single core offering, you have 1,024 ALUs. And so you can use the entire parallel processor to achieve good performance on any new operator, any new model that comes out.
So you've struck a balance here between, okay, we need a certain amount of hardware, software, co-design to a little less on the hardware side and more on the software side so that we can be able to react to whatever changes in the market.
That's right. We do a lot of hardware, software co-design, but the majority of the work is actually on the software side. That is, again, a fundamental decision so that you can react quickly to new changes in software, in AI models, right? We see those changes daily, weekly, and so you have to be able to react quickly our customers have to be able to react quickly. You can't be waiting for the next version of silicon to be able to run a new model.
You've still got changes coming into the hardware piece though, right? So how does that fit together?
Just like any CPU vendor or GPU vendor, we're going to keep updating the architecture itself to be more optimal, more performant for the kinds of workloads we see. That doesn't mean we're taking away anything about the general purpose nature of the architecture. And so at any given point, if there is something that is not running fully optimal because there isn't the specialized hardware for it or the specialized trick for it, then you will always have the software that can run on the entirety of the architecture.
Nigel Drego, thanks for a great explanation.
You're welcome. Thank you for having me.